Okay, so today we're continuing modeling and optimization. So that's why this slide says example/practice, because perhaps you want to do these on your own, and we'll go over them as we always do. But if you're still not so sure of yourself and you want to see me do some more problems, here they are. So this is a little bit different because we never looked at a right cylindrical can. So I'm going to try to draw one. Please bear with all of my drawings. So it says here that the height of the cylindrical can is 4 times the radius. So I'm drawing the height and drawing the radius. And so we got h is equal to 4r. Express the volume of the can as a function of the radius. So volume of this can is pi r squared times h. So right now you can see it's not a function because there are 2 different variables, but if I solve for radius in here, okay, then actually we want it as a function of the radius. Whoops. Okay, so we want v of r. We want to solve for height, and it's actually already solved for. We don't even need to do any work. Woohoo! Okay, don't have a big party. Let's just move on. So h is 4r. And so we're looking at the volume as a function of radius to be 4 pi r cubed. So that answers one part of our problem, but don't forget to answer everything. So if we're to take our first derivative to find the largest or maximum volume it can hold, we end up getting 12 pi r squared. If you take a look at this problem, it's different than the other ones. So we set that equals 0 and go to solve. R would be 0, but r can't be 0, okay? That wouldn't maximize the volume. We'd have no can whatsoever if the radius is 0. So that means that for this answer, okay, there is no maximum volume it can hold. Sorry for my writing. Because as r increases, okay, then the height increases. I'm abbreviating here. It's not like the other problems when we looked at an equation to solve for one variable or the other. Okay, there was like a restriction, like at 120 feet or 108 inches, or whatever the restriction was. Here, it's one variable in terms of the other, but there wasn't like that same restriction. So because as r increases, the height increases, there is no maximum volume. So it actually, in a sense, makes sense. You probably weren't thinking that was going to be the answer, but sometimes that happens. This is another one I labeled as example/practice. I'm only going to do part of it because once I set it up for you, I'm sure by doing some of the other problems, you would be able to finish this, okay? So a rectangular package is to be sent by a postal service. It can have a maximum combined length and girth, and that is the perimeter of a cross-section, of 108 inches with a square base. Okay, this was actually added into the problem. Where I got this from, it didn't say it had a square base, and that is necessary to actually do this problem. So I wasn't sure where this would actually go. So when you look at the wording of the problem, okay, maximum combined means that you're adding 2 things together, of length and girth, L and G, is saying that girth is the perimeter of a cross-section. Okay, so you have to understand what the cross-section would be. So here's your that's supposed to be a box. And the cross section would be when you kind of measure all the way around. So it is a perimeter. And for this particular problem, we need to know that it's a square base. Okay, so if it says here in the problem we want the volume as a function of x. Let me label this as x all the way around. Okay, and so that helps set up my problem a little bit here. So the girth would be 4x, and the length, well, we could actually keep that as L. It doesn't matter. If you want, you could change that to a Y. Volume would be length times width times height. So according to your diagram, or whatever diagram you're using, it would be something squared times another variable. Okay, this is obviously not a function because once again we have more than one variable. So we're going to solve for L here, so it would be a function of x. So if you labeled a y, you're going to be solving for y. So if I solve for L here, I have 108 minus 4x. So now if you look at it, this is just one part of the problem, but now you're going to be able to find the domain like you have in previous problems and the maximum volume. This one you will get a maximum volume. Okay, so continue to work on this and let me know if you have any questions. We're putting this up as practice, so let me know while you're putting it up, before you put it up, after you put it up. That's it. So good luck.